Good evening, everybody. Welcome to 1,000 Shimmering Lights live stream. I say good evening, everybody, but actually, I don't think we'd have any. Don't think we have any audience members just yet. Actually, no. A couple people looks like just jumped in. Cool. As always, if you're watching the show, please say hi in the chat. Let me know that you're here, so I'm not just screaming into the void. But we'll go ahead and get started. Oh, cool. Dad's here. Good evening, Dad. So we'll go ahead and get started now and start with the usual housekeeping and that kind of thing. And obviously, people do watch these after the fact as well. All right. So to get started, I want to remind everybody that this is 1,000 Shimmering Lights. This is my live YouTube planetarium show that I do every third Thursday of the month from 7:30 to 9:30. So if you're watching this after the fact and you want to know when you can catch the next one, that's when you can catch the next one. This is the only live online planetarium show that I'm aware of where you get to be the planetarium director. So all of your questions and comments, any topics you throw in the chat becomes what we discuss. I don't normally plan these things out, although the last couple of episodes have had a theme. I'm kind of returning to form this time to see. I'm actually kind of want to compare it and see how, should I just always have a theme or, what are we going to do? But tonight I'm returning to the usual form of not having a theme. And I will remind you guys that I am the membership director for the Northeast Florida Astronomical Society for now. I am going to be stepping down. I've decided not to run again for the next year. It was never meant to be a permanent position, and I've done it for, I think, like 4 or so years now, and I'm just getting a little bit burnt out, and it's time for someone else to do it. But I have greatly enjoyed being a membership director, and it has been a huge honor and privilege to do this, but the time has just come. But for now, I am still membership director, and even after I step down, I will continue to promote the club on this channel. So if you do live in the Jacksonville area and you are interested in astronomy, you should definitely check out nefas.org. That is nefas.org for Northeast Florida Astronomical Society. We do have memberships. You can go up here to membership and click Join NEFAS and read more about that and join the club if you're interested. Even if you don't join the club, we do a lot of great public outreach programs and things in the realm of astronomy, free to the public and open to everybody. You don't have to be a member to come to our events. And let's talk a little bit about the ones that are coming up. So this Saturday is a possible dark sky night. So I will give a go, no go, and email alert about that this Saturday. Depending on the weather. The weather has not been super great lately, but we will see. Next Saturday is not marked on here, but I think would also be another dark sky night. I'll have to check the lunar phase, but yeah, so it should be because they always come back to back. No real other events going on for the rest of November. And then moving into December, we're going to have our Hannah Park again, first Saturday of December. They've been coming to the beginning of the month lately. They're based on the lunar phase. So it's always going to be the Saturday closest to first quarter moon. And we are not double booked on Saturday. And hopefully I won't be sick again like I was last Saturday. So I should be able to, or last Hannah Park, I should say. So I should be able to attend this one and do my usual laser show. So if you are looking to come to something casual in public, not drive way out to the middle of the woods, and you want to come look through the telescopes, get a live in-person version of kind of what I do on this YouTube channel, though not nearly to the depth that I'm able to do on this channel. But to see me draw the constellations with the lasers, look through the telescopes, and learn about space, I highly encourage you, if you live in the Jacksonville area, to come to our Hannah Park night on Saturday. The time that's listed here is based on when they close the gate. We don't really have any control over that. That's the park. They're polite during the summer and they extend that a little so that we're not just all sitting around waiting for it to get dark. But starting in the wintertime, the gate closes at 5:30. You cannot get back in once you've left, so you must be in by then. The park charges $5, I think, per vehicle, not per person, to enter the park. And we don't charge anything. So come and check it out. And then we're going to have our board of directors meeting next Monday. That's only open to the board and members. Members of the club can come and your voice can be heard. You see how the sausage is made. Wednesday, full moon. And then no general meeting this month of December. Instead, we're going to have a holiday party on Saturday, which is going to be a lot of fun. And then my next live stream is going to be on Thursday the 15th. And as you can see, Not a lot of outreach planned for December either. Obviously, it's a big holiday month. People are spending it with their families. So not a whole lot going on in that regard. Looks like John is here as well. Good evening, John. I do want to also remind you guys that we have another club in St. Augustine that we're really good friends with. Their club and our club. They're called the Ancient City Astronomy Club. Last I checked, their website is still down, but they still exist. You can look them up. You can check them out on Facebook, Friends of the ACAC, Ancient City Astronomy Club. So if you live in the St. Augustine area, you should definitely check out those guys as well. They do a lot of the same stuff we do. They do a lot of big outreach programs, and we go to their programs, and they come to ours. They're a really great group of guys. So if that's more close to you, you should check that out as well. And of course, if you don't live in the Jacksonville area or St. Augustine or Florida or the United States, ostensibly you live somewhere on Earth, and you could find an astronomy club near you, and I highly encourage you to do so. All right. With all that out of the way, let's start talking about the universe. So, like I said, tonight's going to be a return to form. So if you have any questions that are on your mind or just topics that you're interested in discussing in the realm of astronomy, definitely post those in the chat. I don't have a PhD or anything. I'm just some guy that just really likes this stuff. So if there's something I don't know, I always try to be honest about that. But let's learn about the universe together, and let's hang out and talk about space. What can be better than that? So this is my Stellarium program, and it looks like there's some conversation going on in the chat. Cool. Looks like my sister and her fiance are also here. Awesome. All right. So this is the Stellarium software that I use. I always mention at the start of the show that this software is free. I'm not sponsored by them or anything, but I use it, so I give them a shout out. And because I think it's great. I just think it's really good software, and I want to tell you about it. But I don't get any kind of kickback or anything from it. They don't pay me. They should. But there's a downloadable version. There's a phone version, which I think it costs like $2. It's completely worth it. And then there's also Stellarium Web. For some reason, Stellarium Web broadcasts over OBS better than the downloaded version I've found. So that's why I use the web version. I do think the downloaded version is slightly better. But this software allows me to check out the sky. I can time travel to any time of year, so we don't just have to talk about what's in the sky tonight. We can talk about anything. I can zoom in and out, add lines, add artwork to talk about the constellations, the whole bit. Stellarium is also designed by and for amateur astronomers. So rather than just showing you where the constellations are, it will actually indicate where objects are that you can actually observe. You can literally use this to plan an observing session. And it even has a red light mode to protect your dark vision when you're out at night. In this software, the brightness of the stars is represented by the size of the dot. So the bigger the dot, the brighter the star. So now that I've introduced the software and how it works, let's take a look at what is in the sky tonight. So we are moving into late fall and into the winter sky, and I'm going to level with you guys. This is one of my favorite times of year. First of all, as a Floridian astronomer, it's like one of the only times a year where when the temperature plummets, the air dries right up, and you can see right through it, and we're actually able to get a nice, clear, crisp, clean, transparent sky and see all the beautiful stars that are up there. So the winter time is really good for Florida observing, but also a lot of my favorite stuff comes up in the winter time. So let's talk a little bit about what we have. So if we're looking here at the software, you'll see we've got cardinal directions. I'm going to start off in the east because everything rises in the east, and I can already see some really cool objects coming up. One thing that is definitely warming my heart is the Pleiades. The Pleiades is a beautiful open star cluster. It can be seen with the unaided eye, and it looks like a tiny little shopping cart. And it is also the namesake for the car company Subaru. In Japan, they call it Subaru. And it just looks like a really, really, really tiny version of the Big Dipper. If you've ever seen this really tiny dipper in the sky and thought maybe that's the Little Dipper, it's more like a microscopic dipper at that scale, but that is actually the Pleiades. And the Pleiades is a part of the constellation Taurus. So what you should see, if you look east, it's kind of low right now, but it's going to come up as the night goes on, right? Certainly by the end of this broadcast, let me actually jump ahead 2 hours. This is kind of what we would be looking like if you stay for the entire show and then go outside. here we have this reddish star Aldebaran, and there will be several reddish-looking star-like things in the eastern sky tonight because we have Betelgeuse, Aldebaran, and Mars is paying a visit. So if you look to the east and you find Mars, it's right between the tips of Taurus's horns. So to show you how to find that, when you find Aldebaran, you'll find this V-shaped pattern of bright stars. Now, you'll see a lot more stars in the software. If you go out somewhere light polluted, you should see 5 stars, including Aldebaran. This is another open star cluster, even more open than the Pleiades. And Aldebaran is not actually a true member of the cluster. It is a star that is sort of photobombing it. It's just sort of in there with the other stars as if it belongs. But it so perfectly completes the V shape that you would swear that it's supposed to be there. Let's see here. John says October, middle of the month, was quite good for viewing. Yeah, we did have some good viewing earlier this month, or earlier in October, but not as much lately. But once you find that V shape, that is actually the face of Taurus the Bull. If you extend the V, you'll find Elnath and Zeta Tauri, and those are the tips of the 2 horns of the bull, and right between them tonight, you'll find the planet Mars. Mars is having a decently close apparition. It was closer 2 years ago, 1 or 2 years ago, I want to say. I think it was B2. We had that really close perihelion opposition, but this one should be pretty good. One of our club members got a great sketch of some of the surface albedo features of Mars. You can actually see light and dark differentiation on the surface of Mars and even the ice cap. So definitely a good sign that this is a good apparition if he was able to see that through an amateur scope. Oftentimes Mars, it can be difficult to pick out details, but when you get a nice close opposition like this, you really can. I keep saying the words apparition and opposition like almost interchangeably, but they do mean different things. Apparition is from the very first moment that planet's visible into the sky to the very last moment that it is, and opposition is the midpoint. It's when you have the sun, Earth, and then that planet. Let me check in OBS and make sure my hands are showing up here. When you have like the sun, Earth, and the planet are in a line, right? That is what we call opposition. So this one for Mars should be a really good one. Also, of course, if we wait till after the presentation and you head outside, you will see Orion, my favorite constellation. This is personally my favorite constellation. I love Orion. Of course, we got another red star in Betelgeuse. We have Bellatrix, and then we have the famous belt of Orion, Mintaka, Alnilam, and Alnitak. The sword stars below that, and then Rigel and Saif, or Saif. It comes from an Arabic word, so I suspect that it should be pronounced Saif, but everyone kind of says Saif. Fun fact, if you're new to the show, you may not have heard me say this. I say it a lot. Most stars actually have Arabic names. In the Middle Ages, there was a sort of golden age of astronomy in the Arab world, and so Arab astronomers around that time named a ton of stars. A lot of star names and a lot of astronomy we have today comes from that time. We actually owe a lot to those ancient Arab astronomers. But Orion actually has more stars than just the famous hourglass shape. You have this little cluster up here with Mesa forming the head of Orion. And if I add in the lines, you'll see that we have a club or maybe his hand out here. And a lot of artwork depicts this as a lion skin. I've always had that that's his bow because he's a hunter, right? He's reaching back for some arrows. He's got a bow. Obviously, we told a lot of great stories about Orion the Hunter last month in our special stories episode. But today it's enough to simply know where he is. And one cool thing you can look for tonight, this again is another reason why I really like the winter sky, is there's a lot of really good amateur targets, really good visual astronomy, amateur, not difficult yet deep sky targets. And a really good one is if we zoom in here, the middle star of the sword, you'll see it suddenly turn into this big gas cloud, right? So the middle star of the sword hanging below the belt of Orion, if you see, you've got a belt, his sword is hanging below, is actually the Orion Nebula. And it is incredibly close, bright, gorgeous, very easy object. Not like the nearby Horsehead Nebula, which is darn near impossible. The Orion Nebula It's a very easy and very rewarding target, even through a small telescope. Not a very expensive one. It's easily accessible. It's probably one of the easiest deep sky objects to see in the whole sky. So that's a really good one. In fact, I'm talking about a telescope. You can literally look at it through a pair of binoculars. If you get somewhere dark enough, that star will look blurry to your unaided eye. So there's definitely no difficulty at all in seeing that. And the constellation itself, as you can see from the size of these dots, is made up of a whole bunch of very bright stars. Cooper's here. Hey, Cooper, what's up? Just to remind you guys again, as I talk through the little intro that I like to do, where I talk about what's in the sky tonight, that is to give you guys time to think of anything that you might have a question about, or if I make you think of something while I'm talking and you're like, ooh, I'm curious about that, go ahead and start filling the chat with questions so that I will have something to talk about when I'm done talking about what's in the sky tonight. But here in the east, once we find Orion, we can use Orion to find several other constellations, and we can even find what's called the winter hexagon. It's very low in the eastern sky now, but it will get higher in the sky as we move on. In fact, I have to time travel a little bit to show you the whole thing. So this is basically close to 11 o'clock here. 10:40-ish is when we could finally see the whole winter hexagon. If I zoom out a little bit, it will become a little bit apparent. So the winter hexagon, ignore Mars, because Mars is not a star. It's not always going to be there. The winter hexagon is a pattern formed by the bright stars of Aldebaran, Rigel in Orion, Sirius in Canis Major, Procyon in Canis Minor, which is literally just these two stars, Procyon and Gamesa. We have Castor and Pollux in Gemini, which you can see the stars that kind of go down either side here that form the two twins. Capella, which is part of Auriga the Charioteer, which is this big sort of loop of stars. And then back to Aldebaran. We call that the winter hexagon. It's a roughly hexagonal shape of the brightest stars in the winter sky, some of the brightest stars in the winter sky. And if you learn to find the winter hexagon, you have learned to find 6 different constellations. I'll time travel a little bit more so I can show you Sirius. We're going to move on into midnight here. So if you find Rigel, you will find nearby, if it's above the horizon, if it's had time to come above the horizon, obviously I had to go forward in time a bit here. This star here, Sirius, is actually the brightest star in the sky other than the sun, right? Southern constellations we can see from here. That's a good question. Jane, where is here? I'm curious. Do you mean here in Florida? Are you also in Florida? And we want to talk about some of the southern hemisphere constellations that are just visible in Florida? That's a good question. Let me know what you mean by here, and I'll be happy to address that. So, Sirius, it's the brightest star in the sky. If you thought the North Star was brightest, that's not true. Sirius is actually the brightest. North Star is just always north. And when I show it to you in the software, you'll notice that the dot is a lot smaller. If you see anything brighter than Sirius, it is not a star. So Jupiter and Venus will occasionally outshine it, but they are, of course, not stars. Once you find Sirius, though, if I can add in the lines, it'll make it a little easier to see. This is Canis Major, right? So getting rid of the lines again, we can kind of come down here for the front paw. These stars here, here, and here form the head. If we go, Sirius is sort of like on the collar. If we go back to this star, Omicron, and then this one, Wesen, this is sort of like the rear end of the dog. Adhara is the hind legs. And then this star, Aludra, coming off of here is the tail, right? So that is Canis Major. And Canis Major and Canis Minor, which is just these two stars, are Orion's hunting dogs. All right, I'm going to go back to, let's see here. There we go. Going to go back to what the sky is going to look like in 2 hours when the live stream is over. In case you guys want to head outside and look. So that's going to be what we have in the eastern sky. If we move over a bit, first of all, Uranus is in the sky, but good luck. It is not an easy telescope target. If we come over to the western sky, the summer triangle is setting. Right? We see how early the summer triangle is setting. We are leaving summer well behind us at this point. But If you get out early, or if you don't stay for the whole show, which I hope you do, but if you get out early, here is St. Augustine, Florida. Cool, good to know. Also, yeah, Jane, I know who you are. What am I thinking? So, these three bright stars, Deneb, Vega, and Altair, form what we call the Summer Triangle. And those also correlate to three bright constellations in the summer sky. Deneb is part of, if I just add in the lines real fast, Deneb is part of Cygnus, Vega is part of Lyra, and Altair is part of Aquila. And as you can see, this is also a nice bright patch of Milky Way. As we move over into the winter part of the sky, and especially right around by Perseus, we see that the Milky Way fades out almost entirely. So as we move into the winter, the days of bright Milky Way are being left behind. We're getting into the days of a sort of faint, tenuous Milky Way. You can still see it if you get out somewhere dark, but if you are interested in, like, I want to get out and just see the glory of the Milky Way, that time is now kind of in the past. And we're moving on to a time when the Milky Way is not going to be as bright and glorious if you get out somewhere dark. But I do still highly encourage you to get out somewhere dark for some of the other things I'll be talking about. If we do look west, though, the show is going to be stolen by two bright planets. Jupiter is going to be easy to find. Get out, look west. It's the brightest one, right? Of course, as the night goes on, Jupiter is going to set, and as we move further and further into December and then into January, we're going to lose Jupiter completely. And Saturn, we've almost lost. You see how low it is here in the western sky. Still worth a look. And as you can see, it mostly outshines everything near it, but obviously doesn't hold a candle to Jupiter. So once you find Jupiter, start kind of looking for the next bright thing as you continue towards the western horizon, and you'll find Saturn. And I don't need to tell you, those two objects are very easy to spot in a telescope and definite showstoppers. Even a very inexpensive telescope is going to show you the rings of Saturn and the moons of Jupiter, and they are both very worth it. Highly, highly recommend. One thing that we have, and you have to basically look almost straight up to get to it tonight. If you look, we have this M-shaped group of stars here. Kaf, Shadar, Gamma Cassiopeia, Rukba, and Segin, if I'm pronouncing this correctly. And that is Cassiopeia. If you find Cassiopeia, it looks like a big M. It's a fairly bright constellation. As you can tell when I delete the lines, it's still easy to see. And if you find this constellation, you'll notice it's shaped like an M or a W, depending on how you look at it. But one of the peaks of the M is nice and tall and thick, and the other one is sort of thin and short and squashed. Find the tall one, shoot through that arrow, like an arrow through a bow, and you will hit this reddish star here called Merak. Once you find Merak, you can go 1 star, 2 stars to the left, and this third star here is a fairly small dot. It may be hard to see, especially if you're somewhere light polluted, but next to that is the Andromeda Galaxy. You'll see the software calls it Andromeda Nebula. That's a sort of traditional kind of name before we learned that the spiral nebulae were actually other galaxies. But most of us call it the Andromeda Galaxy these days. And it is another very easy amateur target. It's the easiest galaxy to see by a long shot. And I have shown it to people from downtown Jacksonville. Mind you, downtown Jacksonville, we were just barely able to see the core, not the whole thing, but that should still give you an idea of how accessible it is. If you're anywhere even a little bit dark and you have even a moderate telescope, it's well within grasp. It's, as far as deep sky objects go, it's a very easy one and a very good one to go after. Something else you can check out in this piece of the sky is once you find Cassiopeia, and you find Perseus, which is this sort of Y shape over here of fairly bright stars. About halfway between the two, you may notice something sort of blurry in the sky. That is what we call the double cluster, and it is actually two clusters of bright stars. It'll give the software a chance to catch up and really show what they really look like. They're next to each other. You can see them both at the same time through one view in the telescope, and that's another great target to go after. Especially if you're just getting started in the hobby and you're looking for easier targets, you kind of can't beat that one. Okay, now, let's see here. We did have somebody ask, can we talk about some of the southern constellations that can be seen from St. Augustine? That is a really good question. Um, let me see if I can. Let me see if I can change the settings. See, the only problem is, can I? Oh wow, you can log your observations in Stellarium Web. That's cool. Calendar. I don't know how to change my location. Oh, here it is, near Jacksonville. So let's zoom out a little bit. Oh, gotta zoom in a little bit. We're gonna plop that down. Use this location. We are at Barrios Pizzeria in Beer and Wine Garden. Barrios Pizzeria, Beer and Wine Garden. Congratulations, you have gotten free advertising from 1,000 Shimmering Lights YouTube planetarium show. This is what the sky should look like near St. Augustine, and it shouldn't look all that terribly different from what we have up here in Jacksonville. Now, of course, if you want to see southern constellations, you need to look to the south. And I'll be honest, I'm not super strong on my southern constellations, so we're going to add in some artwork and find them. So, about right here, cutting through Eridanus, below Cetus and Aquarius, and Capricorn, is this sort of, if we could just sort of imagine a line right about through here, is where we start to divide the northern hemisphere constellations from the southern hemisphere constellations. If you imagine, if you know the Earth is a sphere, right, and we're up here looking kind of this way and all around here, obviously if you're down here, you're going to see entirely different stars. So the southern hemisphere has its own entire set of constellations that we don't have in the north. But, let me get rid of that. But we can, because we live in Florida and we are so close to the equator, low on the horizon, we can catch some of these southern constellations. Grus is one of them, which I want to say is like a goose or something. I'm not really sure. This is a crane. Okay, the crane. Phoenix. There's a constellation of the Phoenix down here. Piscis Austrinus and Fomalhaut. That is a star we often see from our observing location out at the swamp. Not sure whether this is considered a southern hemisphere constellation or not. It lies right on the border. Piscis Austrinus is the southern fish, right? So if we add in the constellation artwork, that is a fish. And it's kind of appropriate because it's sort of close to Pisces up here and Aquarius over here. We have Sculptor, right? And you can kind of see that down here we have things like Coelum, which means chisel, apparently. That's interesting. And Horologium. What is Horologium? It's a pendulum clock. So one interesting thing about the southern hemisphere constellations is we have things like Microscopium, for example, right? And Sextant and the clock. And that's because a lot of these constellations were named by explorers in around the time of like Columbus and those guys, or probably before, more like Magellan and those guys, sailing around in the southern hemisphere and seeing new constellations that they didn't know anything about. And there are people who live in the southern hemisphere, of course, indigenous people who had their own constellations. But historically, the Europeans, obviously, there's a great European bias, and a lot of the constellations that are now official kind of come to us from these European explorers. And so they put things in the sky like microscopes and sextants and clocks and some of these things that did not exist back when the ancient Greeks were naming their constellations. I'm going to time travel a little bit to get to February because one of my favorite southern hemisphere constellations right here. First of all, we have Centaurus, right? Centaurus, the centaur. And we have, you'll notice this big ship coming up right here, right? And here's our good friend Canis Major again. We got the big dog again right over here. And below it, we have this thing called Puppis. Now, this used to be one enormous constellation. And I'm actually going to switch all the way down to South America so we can get a good look at it. Because not only can we travel in time, we can travel in the world. All right. And boy, I lost it. Here it goes. So this whole thing used to be a gigantic constellation called Argo Navis, which is the ship, the Argo, right? The Jason and the Argonauts. Because the International Astronomical Union utilizes. Oh, that is really cool looking. Why don't we have that up here in the north? Because the IAU utilizes the constellations to break up the sky into actual like territories. So essentially, there are borders around the constellations, and when we identify objects in the deep sky, we would say that object is in this constellation or in that constellation or what have you. Argo Navis was too big to be useful for that. It was too much of the sky in one constellation. So it was more useful to break it up. So the IAU now recognizes three distinct constellations in this area. Puppis, which is the keel of the ship. Vela, which is the sail. And Carina, which is the hull of the ship. Right? And, oh, I know what this is over here now. Yeah, okay. So, this is why this is probably my favorite Southern Hemisphere constellation. First of all, it's one of the few ones I've had the pleasure of seeing. I've never actually been to the Southern Hemisphere, but I have been to the Florida Keys. And let me show you what our view from the Keys looks like. Move over there near Cuba real fast. And I will actually put us on the exact spot, too. Give me a second here. This is a good question, Jane. This is actually a pretty fun topic. I'm enjoying this. All right, I'm moving in here. There's Key West, so we're getting close. Okay. All right, here's Highway 1. So, where is Marathon and Big Pine? Have I gone too close or too far? Maybe. I remember seeing signs for the Key Deer Refuge. Oh, there's Florida, or there's Marathon. Okay. I'm gonna move over here. There's the 7 Mile Bridge, yep. And at the end of the 7 Mile Bridge, this little guy right here, and then Bahia Honda. So this must be... I'm thinking right in here is where it is. That's Little Duck Key. Missouri Key. I'm just going to put us on Little Duck because I don't want to spend all night trying to find it. But somewhere on one of these tiny little keys is what we like to affectionately call... Oh, no, I found it for sure. This has got to be it. Okay. We call this Scout Key because the only thing that's really on it is a Boy and Girl Scout camp. Right? So right here... Yeah, this has got to be it. This is the campsite. And I could probably even put you exactly where my tent was. Like right about here, I would say. Yeah, somewhere around in here. So we're going to use this as our location. So this is what we'd be looking at in the Keys. And this is around the time of year, February, around the 14th and so, that kind of week. And you would get out at night and you could see Vela and this coming up. And if you waited till like 1 or 2 in the morning, you see how it doesn't get very high. But right down here is this pink thing that you're looking at. What on earth is this? This is the Eta Carina Nebula. It is 4 times the size and I think double the brightness, apparent size that is, and double the brightness of the Orion Nebula. It is an incredible, incredible nebula to observe through a telescope. It was like seeing the Orion Nebula for the first time again. It absolutely blew my mind when I saw that down in the Keys. Right. And the reason why I was down there, and I've gone down there a couple of times and hope to go again, is for something called the Winter Star Party. They do this every year. They couldn't do it the last 2 because of COVID, but they're bringing it back. And people from like all over, literally I met a dude from Germany. I got to practice my German while I was down there. One time I was camping next to a guy from the UK. It's a really cool place. And it's, there's hundreds of astronomers. We take over this whole island. And we're all there to do astronomy. And you see all kinds of stuff. One guy had a telescope 32 inches across. The aperture was 32 inches. Absolutely mind-blowing. I got to look through it. It's incredible. And because you're so far south, you can actually get objects that you normally can't get from Jacksonville, like the Eta Carina Nebula. And then this next one, we do get it sometimes out of the swamp, but it's difficult. Right over here, we call this Omega Centauri. It's another incredible object. The biggest, um, the biggest globular cluster visible in the northern hemisphere is the Hercules cluster, M13. This thing eats it for lunch. This is an absolutely enormous globular cluster. You can see I didn't even have to zoom in very far, right? And you already see it's just this giant, absolutely huge swarm of stars, right? It is such a huge globular cluster that it's thought that it might actually be the leftover core of a galaxy that got destroyed by our own galaxy and incorporated, right? That it may not be like a globular as such. And of course, you get to see the Southern Cross, right? And the astronomical club down there in the Keys is called the Southern Cross Astronomical Society. And of course, their theme song is that Jimmy Buffett song about seeing the Southern Cross for the first time. They play it like a million times. That when you're down there, you're gonna be humming it by the time you go home. And obviously, you gotta see it, right? I remember the first time I went down and I found the Southern Cross and I was excited. And the next year I went and we had some people with us that hadn't been before, and I got to show them the Southern Cross. It was really cool, right? It's like one of the things you got to do when you go down there. You got to see the Southern Cross. You got to see Omega Centauri. You got to see the Eta Carina Nebula. You got to go eat fried key lime pie. I forget that restaurant. You got to eat. You got to go to Mickey's Kitchen at 2 a.m. and get piping hot fresh brownies. And everything is funny at 2 a.m. when you've been up all night stargazing. And you got to, I forget his name, but there's a guy down there who like runs all the kayaking tours and stuff. And every year you can like buy in, and he does like a big stone claw feast, right? And for me anyway, you got to do that when you're down there too, right? These are all like the Winter Star Party traditions you have to do, and of course, and then observe the whole rest of the sky. But these are some of the things that are visible. But if I get back to Saint Augustine. And no telling if I'm going to accidentally find that same pizzeria again. That would be really funny if I do. But I'm honestly tempted to search it and make sure we're back at that pizzeria again. But no, I'm just going to plop this right down here in St. Augustine. Oh, the Castillo de San Marcos. I couldn't have picked a better thing. If you're watching this show and you're not from Florida, the Castillo de San Marcos is an old Spanish fort down in St. Augustine. It's made of coquina, like basically shells that have been compressed into stone. It's one of the big star-shaped forts, but it's got 4 points. It's really cool. Anyway, and so you can see Argo Navis, Pyxis, Antlia, Centaurus are all visible from there as well. Excellent question, Jane. Thank you so much for asking. And Jane in the chat, she agrees. And have some brownies. You got to have some brownies, right? So the Mickey's Kitchen is this like food truck. Apparently she goes around to a few of the star parties, right? And her food truck, they take it in shifts so that it's open 24 hours a day. And they have all red interior lights. So even at night, the food truck is observing proper light discipline, just like all the astronomers. So you can go up and order food without ruining your night vision and get right back to observing. And like starting at like 1 a.m. or something, she bakes fresh brownies. And that's one of the best things, man. You've been up all night observing, and you're going to keep being up all night because obviously you spent a bunch of money to come down here and be a huge nerd. And you go and you get the brownies and you're just hanging out under the awning nearby where they got all the picnic tables set up and eating the brownies and talking about the things you've been observing and what you're going to try and observe and Kraken wise and whatever. It's just part of the experience, man. It really is. I haven't bought my ticket yet. I got a lot going on. It's not cheap, but I'm hoping I'll get to go again this year. Maybe I can convince everyone to pitch in and buy me my Winter Star Party ticket for Christmas. Hint, hint to my family members watching this. Maybe. I don't know. It's a big ask, even if they all pitch in. It's not cheap, but it is worth it. If you haven't gone, I highly, highly recommend it. Let's see here. So we've all been talking about the southern sky for a little bit. Does anybody have any other... Oh, yeah, Dad asks, what is Pyxis? That's a good question, man. What the heck? Oh, it's a compass. It's the constellation of the compass is what it's supposed to be. And I guess that's kind of appropriate because it seems like it points toward the southern pole. ish. But that's what it's supposed to be. Like I said, a lot of these things are like, what the heck is Antlia? I have no idea. What is this supposed to be? It's a pump. It's an air pump, right? These are things that would have been important to sailors in the southern hemisphere. I mean, granted, you also get like a centaur down there, but for the most part, it's like ships and navigational tools and things that would have been important to these sailors going down there. All right. Oh, also, where is it? I'm just gonna try and find it. Oh, here it is, Gamma Valorum, also called Rhaegor. If you've ever watched The Orville, right, the one that's basically like Star Trek, there's an episode where they go to Gamma Valorum, and they refer to the people who live there as Rhaegorians, and that's why. It's literally that star. I love when Star Trek and The Orville and shows like that use real stars, right, to talk about these things. I'm going to stay in the Castillo de San Marcos. This is kind of a cool place to observe from. All right. Well, I did the tour of the sky there. Does anybody have any questions about anything? Any topics that you find interesting? What is Pixis? All right. Here's what I'm going to do. I did prepare a little bit in case there was a lull. So one topic that I think is interesting, excuse me. The weather has been wreaking havoc on my throat, so more than ever, I need to be constantly drinking. Thank you so much, Jane. So, appreciate you too, man. So let's talk a little bit about stellar distances, right? Measuring things in space. So this topic came up because I had a few situations where I was talking to people and they would think that something was really far away or not as far away or whatever, and there's some confusion over distance. But also, how do we know, right? Like, how do we know how far away things are? It's actually a very fascinating and complicated subject. And I'm not quite qualified, but we can dive into it a little bit, I think. And while we're talking about it, again, maybe some questions or some thoughts will occur to you of some things we can talk about. Because I didn't plan anything. This is your show. But, yeah, the question is, how do we know how far away things are, right? So one unit of distance that we use, and I'm going to switch to visuals here. And actually, you know what I'm going to do real fast? I should have done this before. I'm going to actually show you those objects I was talking about. Omega Centauri. I'm using Wikimedia Commons here. I'm going to try and point out the proper attribution of the images that I use. Here it is. Properly attributed to Pablo Budassi. I hope that's sufficient for using it on the Wikimedia Commons. I don't know the exact licensing of all these images. It's got the share alike license, so hopefully that's sufficient. I'm not monitoring this. Please don't sue me. But this image right here, this is Omega Centauri. And man, this should give you some notion. These specs, these aren't like, this isn't like pixelated, right? This isn't somebody spilled a bunch of dust on something. Every single dot in this picture is a star. Just every last one of those dots in this bright area in the middle, where it looks like it's just glowing, it's just because there's so many stars we can't pick out any individuals, right? Look at that. Isn't that something else, man? There's a bit of a story I got to tell you about Omega Centauri. When I was down in the Keys the first time, right, for the Winter Star Party, one of the first nights I was like, I'm going to see the Eta Carina Nebula, right? As you guys, some of you guys who watch the show a lot, or people who know me in person know, I like to sketch everything I observe. And one of the club members was like, man, when you get down there, I can't wait to see your sketch of Eta Carina. And I will show that to you guys if you want to see it. But I was like determined to see the Eta Carina Nebula. This is an interesting picture, by the way, because I can tell he cropped out everything that's not this cluster. Let me actually grab... Yeah, I'm not making changes, man. That's not mine. All right. So this would be like it in context, right? With everything around it. So, okay. So I'm going to stay up and watch. Golly, though, look at that thing, man. Oh, man. Holy smoke. So... I'm like, I'm gonna observe the Eta Carina Nebula, right? And I had asked the guys, I was like, how do you see it? When do you see it? And whatever. And they're like, yeah, you got to get up at like 2 a.m. or whatever. So I was like, okay, cool. So I set an alarm on my phone because, the night before I had done that big long drive and I did sleep, but I was still like, I'm going to get a little sleep and I'm going to wake up and observe it. So I get up and it's like 2 and everyone's already gone to sleep. Right? Nobody's still out observing. And I went and I'm sitting at my telescope, kind of like waiting for people to come out, and I don't know where the heck to look for this thing. And I got charts, but I was like, well, let me just take out my binoculars and goof off while I wait for the other people. So I got my binos, and I'm like just sweeping, just looking at stuff, looking at the ships out on the water, sweeping around. I almost dropped my binoculars. This thing, when I came across it, I literally just I went, that's Omega Centauri. I had never seen it. I didn't consult a chart, anything, but I knew from reputation that there's no way that could be anything else because it was so huge, even in a pair of binoculars, and just absolutely mind blowing. I almost dropped my nice 15 by 70 astronomical binoculars. It was absolutely stunning. And then later, it keeps asking me if I want to save my changes. Later on, make sure I'm spelling this correctly here. Eta Carina. Yeah, later on I got to see this guy, the Eta Carina Nebula. We find us a good picture of it. This is a really good picture right here. Right. Oh, hold on. Let me make sure I get the proper attribution. Where'd it go? Harold Boren. Creative Commons license. There he is. There he or she is. Good job, Harold. This is a great image. All right, so this is the Eta Carina Nebula. Through a telescope, you will see mostly this part of it. Obviously, the outer bits are going to get a little faint. But like these dark dust lanes, yeah, 100% you can see those through a telescope. This little thing right here in the middle that we call the keystone, right? This is kind of what it looks like through a telescope. You're kind of zoomed in on just this part. It's so big, it's hard to fit the whole thing in the view. I actually had to borrow an eyepiece that had a wide enough angle to get the whole thing. This reddish star here is Eta Carina itself. It is a red giant that is like right on the cusp of dying. It's going to die any day now. Of course, it's going to die any day now for like the last couple thousand years, but you never know. This thing is just absolutely jaw-dropping. Now, it looks pink in this picture because it's an H2 region. Hydrogen glows mostly in that pink color when it's ionized. But there are other colors in that light as well, because there are other components to this gas cloud. If you look, you'll probably see that it looks a little... and yes, you would enjoy seeing the sketch. Cool. We'll talk about that too. You'll see that there's definitely some purplishness and stuff going on here, and that's because there's also ionized oxygen in there. That is adding in a teal color to the pink. If you use an O3 filter to observe it, you're going to only get that teal color, right? So let me see if I can... Yeah, I think I could just pull up just a plain old image, right? So give me a second here. Because then I can show you some of my sketches here. All right. I'll show you I did get a sketch. I went back later with the telescope and got a sketch of the Omega Centauri cluster. And I just about wore out my pencils going adding all those stars. Like I keep joking around. One of these days I'm gonna get like a styrofoam holder and just fill it full of mechanical pencil heads and call it my globulizer. So when I'm doing a globular cluster, just be like, and get more of them done at once, like a tattoo needle. Boy, it has taken a second to load this image, and it is currently crashing my software because I do all my sketches and I scan them in pretty high res. But goodness gracious, did I crash this thing entirely? Oh man, we do not want to close the program. That will close the stream entirely. Oh boy. Oh man. Okay. If you guys lose me suddenly, if you haven't already, my planetarium software has, or my streaming software, I should say, has crashed entirely. That should even... I don't know what the right answer is here, because if I don't do anything, this is definitely crashed, and if I do, see, and it'll end the stream. If the software closes, it'll end the stream. But okay, I think I managed to do that without having to restart the stream. Right? Are you guys able to see me now? See me and hear me? Hopefully. I know there's a slight audio time delay, so if you don't respond right away to me, I'll know that's what it is. But in the chat, let me know if we're back, if we're live again. And let's see here. Gotta restore my visuals. There we go. Okay. All right. I'm not sure I'm going to be able to show you my pictures. What I might have to do is make some lower res versions and maybe show them some other time. But unfortunately, well, I'll tell you what. I'm going to try it again. Maybe it just, I don't know. Maybe it just acted weird. I'm going to try it again. Since I know I can recover the stream if I need to. But yeah, man, no doubt that I do high resolution scans of my sketches because I want to make sure I had the best possible version of it for when I, edit it later and all that kind of stuff. Okay, I'm not gonna touch it this time. I'm just gonna let it load. That, I think, might have been a mistake. Yep. Oh, God. Okay. Should be back again, hopefully. Yeah. So good to know I can recover the stream if I need to, but clearly trying to show you guys those pictures is crashing the stream. So sorry to say, I'll have to think of something because I've shown my sketches on here before. So that's kind of weird that it doesn't want to do it now. But I don't want to like take the risk of like just crashing again. Right? But I guess it is what it is. So, anyway, all that to say that they are incredible, incredible things to view. And I guess since nobody said anything else other than wanting to see the sketch that I unfortunately can't show you, I will go ahead and move on now and talk about distances. That's what I was going to talk about. So, when it comes to measuring things in astronomy, we have this thing called the cosmic ladder. And it's actually kind of complex. Let me see if I can bring it up on the screen for you real fast. Oh, let me make sure I attribute this image correctly. All right, so this one, Bruce O'Hare, Creative Commons license. So this is the extragalactic distance ladder. So this is actually only part of the distance ladder, dealing with things outside the galaxy. There's a whole ladder for within the galaxy as well. But these are all techniques that can be used to determine distances to objects. But what's really cool about the ladder that you've probably seen is all these arrows going to the things, because each rung on this ladder only works because of things we learned from the previous rung, right? We're not going to go over all of this. This is honestly nuts. But we're going to talk a little bit about some of the first couple of rungs and some rungs we can wrap our heads around pretty easily, right? So the first thing we have to figure out, right, if we want to find out where anything is. Yeah, John's saying I might need to make a more lossy JPEG. Yeah, for sure, right? But if we want to find out where anything is, we first need to know we need to be able to measure something, right? And really what we have to be able to measure is the Earth's orbit. And I'm going to explain in a second why that's the linchpin that everything else is based on, right? But we have to be able to measure the size of the Earth's orbit. So the Earth, let's see here. Let's take this one. This one looks good. Yeah. Cool. All right. So this is by CM Glee. Creative Commons. There's all the information there. And this is not what I'm looking for, actually. Hold on a second. Because this, I just realized, is the Earth itself and where a bunch of satellites are orbiting. I mean to say the orbit of the Earth around the sun. Is this going to be it? No. This is fine. This is honestly, it's a cartoon, but it'll be fine. Tao Lunga, thank you so much. Creative Commons 0, public domain dedication. Ooh, that's nice, public domain. Now we're talking. All right, so obviously the Earth isn't nearly this close to the sun, but we need to know how far the Earth is from the sun. And that distance measurement from the center of the solar system to the Earth forms the basis of all the other measurements in astronomy, and we call that 1 astronomical unit, right? Because it's 1 unit in astronomy. So how can we figure this out? Well, what we can do is we can bounce radar signals off of other planets and figure out how far away from them we are. That sounds kind of crazy, but it can be done. You fire off a pulse of light, the pulse of light, or of radio waves, basically, and the ones that bounce back off of that planet, you know, we can count how long that takes. We know the speed of light in a vacuum, so there you go, right? And we can figure out how long that takes. We can figure out how far we are from Mars, Venus, etc. And of course, we're going to want to do these at points of opposition, right? So we have a Mars opposition, bounce that, find out how far Mars is, do that several times, get a good idea of Mars's orbit relative to ours, right? Same thing for Venus. And then what we can do is when Venus does a transit of the sun, right, we can use some geometry to calculate Venus's position relative to the sun, right? So it's actually easier to figure out Venus's orbit than our own. But once we have a good idea of Venus's orbit, and we have a lot of measurements of our relative distance to Venus every time we're in opposition with it, then we can figure out how big our own orbit is, right? And so that's how we know that 1 astronomical unit is about 93 million miles, right? That's about how far we are from the sun at any given point. Sometimes a little less, sometimes a little bit more. That's about the average, rounding it off substantially to say about 93 million miles for the sake of our conversation. Now, what's cool about that is that once we know the Earth's distance from the sun, then we know that if we take opposite sides of Earth's orbit, we just double that distance. And that's how far the Earth goes laterally, right? When Earth orbits, its maximum side-to-side movement from one end to the other end of the orbit is 2 astronomical units. Keep on to say union, like the astronomical union. 2 astronomical units, right, for that complete thing. Now, why is that good to know? Well, that's good to know because of something called stellar parallax, right? So, using this image, this is a NASA press release, so I'm sure they won't mind. But here's all the attribution here. It's public domain. So, when we look at a distant object, so to explain what parallax is, if you don't know, if you're driving on the car and you look out the window and you see the telephone poles are just whipping by, and then that house in the distance is just sort of crawling along, and that mountain way in the distance almost looks like it's not moving at all, right? That's parallax. Nearby objects will change position more dramatically as you change position because your angle of vision is altered more than for a much, much more distant object. It's going to be less altered, right? So that's parallax. So if you look at a distant object and you move a known distance, like you say, you look at an object in the distance, you look at it relative to the things behind it, right? If you could find something behind it far enough away that it appears not to move, then if you move and that object moves against its background, you can calculate the angle, the change in angle, and that will tell you your movement is the base of an isosceles triangle, and then the triangle has to intersect at that object and then continue through it to account for that motion of parallax, right? That's shown on this chart. So if we look at this chart, you'll see that when the Earth is here, the object appears to be over here. When the Earth is on this side, the object appears to be over here, right? The angle of this difference is going to be determined by how close this object is. The closer it is, the more it will appear to move. The further, the less. And there's very precise, very reliable geometry behind that. It's just geometry. It doesn't change. It's not anyone's opinion. So if we know how far an AU is, we know the size of the base of that triangle and can therefore do the math to figure out any of these other things, right? Because if we find the difference between these two, we're like, okay, the angle changed by X. If we don't know the size of Earth's orbit, that doesn't mean anything to us, right? Because Earth could be going a really long distance, and so then that would be one number, or a much shorter distance, that would be a different number. But because we know the size of Earth's orbit, right, that was the first rung on this ladder, now we know this. And so we can tell that if it's moving further, that star is closer. If it's not moving as much, that star is further away. So stellar parallax allows us to identify objects that are close by, right? And this is actually going to introduce a unit of measurement that astronomers are very familiar with, but I think members of the general public are not nearly as familiar with, and that is called a parsec. If you've seen Star Wars, you've heard it. Han Solo brags, the Millennium Falcon could do the Kessel Run in under 12 parsecs, and that's gibberish because a parsec is not a unit of time, it's a unit of distance. And it actually stands for parallax of 1 second of arc, right? So when we measure angles, right, you have 360 degrees is a complete circle, right? The sky is going to be half of that, so it's 180 degrees. Each degree is made up of 60 arc minutes, or minutes of arc, and each arc minute is made up of 60 arc seconds. That's how small of a unit we're talking about. And a parsec is how far away a star has to be so that as we complete one orbit, it appears to move with a parallax of 1 second of arc. That is the unit we call a parsec, right? And a parsec happens to be a little over 3 light years. It's like 3.20 something light years. I'll have to look it up real fast. Let's see here. Google parsec. Okay, parsec unit. It's about 3.26 light years, right? That's how far a parsec is. 3.26 light years. So, we know, and we could calculate the distance, and we know how fast light travels. That's why we know it's 3.26 light years. Astronomers actually, professional astronomers rarely measure anything in light years. They're actually doing everything in parsecs. But light year is a unit of measurement that's easier to explain to everyday people than a parsec. You saw what I just went through to explaining what a parsec is. Whereas I could just tell you, yeah, light took that long to get there. And that's really good for like public science promotion, right? Science popularization. You can tell people that like the light from that star took 8 years to get here. I do that sort of thing when we do our things. But if you're curious, for real science, we're actually measuring things in parsecs because it's based off of this, right? And then you can always convert that to light years, right? I say we. I'm not doing this. This is well beyond my pay grade right here. But so this gives us a rung on the ladder. So we got the first rung is we need to know how big the astronomical unit is. Second rung, now we know how big a parsec is. And then what if the stars are too far away to determine their parallax? Are we just up the creek now? We have no idea how far away they are? Well, no, because we can go to another rung. Because now that we know how far away a bunch of nearby stars are, we have something called the inverse square law, which says that light falls off as the inverse of the square of the distance. So you square root, square root, square root, square root the amount of light over distance, right? So it's a logarithmic thing. It kind of plummets. So the further away something is, the dimmer. That's the simple version. You can run the inverse square law in reverse, and you can figure out how bright the object really is, right? If this is how bright it appears to be, and we know now how far away it is, we could figure out the intrinsic brightness of that star. We now know how bright that star actually is. Okay, so in addition, we know a lot about the composition and nature of stars. So even if we don't know the distance to a star, by analyzing the light, we can break up the spectrum of the star. We can figure out what type of star it is, and then we can figure out how bright it should be, and use the inverse square law to figure out how far those are. And that works out to a certain distance, right? So now we have another rung on the ladder. We can use the inverse square law and the brightness. Now that we have a good understanding of stars nearby and what we should be looking for, we can look a little bit further. Now, doing this with nearby stars with parallax and nearby ones that we can do with the inverse square law, we can then learn that there are different kinds of stars that will vary in brightness over time, right? So there are RR Lyrae stars, there are Cepheid variables, and these stars will brighten and dim, and brighten and dim, and brighten and dim, right? Like clockwork. And what's cool about them is that the period of time between two peaks in brightness correlates directly with the intrinsic luminosity of that star. Meaning, the brighter a Cepheid variable star is, the longer it is from the brightest period to dim all the way down and go all the way back again, right? That wavelength in that pattern of brightening and dimming is determined by how bright the star is, right? Intrinsically, right? So it means that we could find a whole bunch of these nearby ones, learn their intrinsic brightnesses, look at that thing, and then astronomers found that correlation. And that correlation holds true. Which means that if we find Cepheid variable stars that are so far away that the techniques we already have for measuring their distance are difficult to do, what we can do is just time them. Watch them day after day and see how long does it take to dim and then brighten. Now we know how bright the star actually is. Now that we know how bright the star actually is because of the parallax, because of the astronomical unit, we can use the inverse square law and we can figure out how bright it appears versus how bright it is. We can use the inverse square law and find out, oh, it is this far away. And now we know how far away that Cepheid variable star is. So now we have another rung on the ladder. If we want to find out how far things are, if we could find any Cepheid variables, then we are not at the mercy anymore of parallax. We can climb the next rung. So this is the thing I wanted to basically get across, is the way the cosmic ladder works is that we steadily climb these rungs, and here we have the Cepheid variables now on the ladder, right? There's a color coding to this ladder, and I forget what they are. It's like certain of these are like direct observations, and certain ones are only good for certain things. But you'll see a lot of these like RR Lyrae globular cluster, right? We can figure out the globular cluster, how far it is, because if there are any RR Lyrae stars within that cluster, then we know how far the whole cluster is, because all the stars in the cluster occur together, right? And then we could figure out the distribution of globular clusters, and then we can look for that. We can look for RR Lyrae stars in the local group of galaxies and figure out how close all of our neighboring galaxies are, right? The Cepheid variable is what Hubble used to figure out that the spiral nebulae are in fact other galaxies, because he realized he could measure how far away those nebulae are, and he determined that they were too far away to be part of our own galaxy, right? That if you take individual stars in our galaxy and you measure their distance by any of the rungs on the ladder, they are nowhere near as far away as the Cepheid variables he found in the Andromeda galaxy, right? Those are 2.5 million light years away. So he reasoned that that was its own disk of stars separate from our own. How did they figure out the magnitude of a star? What do they use to measure it, especially long ago when they set the magnitude ratings for stars? That is a good question, and I'm glad you asked it, because I kind of ran out of things to talk about on the cosmic ladder because I don't really understand much of it above a certain point. One last thing I will say is that another thing that Hubble figured out is that the space between galaxies itself is expanding, and it causes the light from distant galaxies to shift into the red, and the amount of that shift correlates with distance. So now we have another rung on the cosmic ladder. So once things get a certain distance away, we can just look at how redshifted they are. And because the Cepheid variables work, and because we know that they work because of the inverse square law, and because we know the inverse square law and the Cepheid variables work because we measured light fall off of other similar stars. We know that works because of stellar parallax. We know stellar parallax works because we have the astronomical unit, right? All of that, all of those things check out. So now we can just skip right to the redshift. We can just use redshift to figure out how far things are. But it's all bootstrapped from the previous rungs, which I think is really neat. Knowledge begets more knowledge, right? So how do they figure out the magnitude of stars? That's a good question. I don't know the answer to a I don't know the answer very strongly, but I do know that there is one thing that I know that was done. There was an astronomer who basically took a brass disc, and I don't recommend doing this. It sounds like a great way to ruin your eyes. But he took a brass disc and he drilled different size holes in it, right? And held it up and blocked the sun with it, and looked and saw how bright the sun looked through each of those holes, right? And because of the properties of light, the smaller your aperture, the dimmer the light will be. So by shrinking the size of those holes, he was able to create definitive dimnesses, basically, and was able to kind of do the math and figure out. And he basically set his, oh no, sorry, I'm mixing things up. The magnitude scale, the guy who came up with the magnitude scale, I think he just invented it. He was just like, the brightest stars, he just called them first. And it wasn't very set in stone originally. It was like, he just basically made 6 classes of stars. But what you can do, and what they used to do back in the day when deciding was this going to be first or second or third magnitude or whatever, was to compare them to nearby stars. So if I remove the visuals here, right? So if we say that, Sirius is a first magnitude star, and actually Sirius it's a -1, right? Let me see if I can find a good first magnitude. Maybe Procyon. Procyon is actually like a half a magnitude. Pollux might be a good first. Castor is 1.5. Capella is 0.24. Man, there's a lot of bright stars in this part of the sky. Anyway, if we're going to use Pollux as like a 1.5, then what you can do is you can kind of look and see the nearby stars and say, is that half as bright? Is that a third as bright? Right, etc. And the magnitude scale was logarithmic. So anything that was first magnitude, second magnitude stars would have to be 1/10 of the brightness, right? And then third magnitude stars would have to be like 1/100th of the brightness. A trick you can do with a telescope that would have been done back then as well is you can rack it out of focus and turn all the stars into big disks, and then they're easier to compare, right? And then the brass disc I'm thinking of, there was a guy who did that because he suspected that the stars were other suns, and so kind of like drilled holes representing different distances and basically tried to like figure out which one looked like a star. And this was one of the earliest attempts to figure out the distances to other stars, because he basically was like, if these were other suns, they'd have to be incredibly far away, because I had to drill a really tiny hole for it to look like a star, basically, was what he figured out. That's the best I know on that topic, to be honest. John is saying purely by observation, then photometrics were used to precisely measure. Yeah, so later on we had photometrics. You could take imaging, and measure the wavelength. But originally it was all done by eye, and it was all done by 1-to-1 comparisons, right? This star and this star, how bright is it compared? Okay, what about these two, right? Well, how does that compare to that, right? And they were all just sort of figured out relative to each other and assigned these magnitudes. And it is a backward scale. The smaller the number, the brighter it is, kind of like earring gauges. Right? The smaller your gauge, the bigger your earring, your big hoop. So, first magnitude was a cool thing to call the brightest one, and then the second magnitude of stars with the less bright. But it does mean that now it's kind of confusing that the small numbers mean brighter rather than the other way around. That is another excellent question from the audience. And again, apologies I couldn't give a more thorough answer than that. But like I said at the beginning of the show, I always try to be honest about what I know and what I don't know. And I don't want to talk too much about that which I don't know. Yeah, John's saying it's a logarithmic measure. Maybe you guys are logging pretty far behind. I'm not sure. Let's see. Does anybody else? I'm going to give you guys a second. Does anybody else have a question for me? today at work, I was training some of the trainees that I work with, and some of them were like, "I want to watch your show." So, don't know if maybe they're just not able to log in and comment, or if maybe they're not watching it. Who knows? But if you are watching this, and I am training you at work, I'll see you tomorrow and train you tomorrow. But if you have questions, definitely post them in the chat. Also, anybody watching this, if you're not able to chat on YouTube, but you know some means of getting a hold of me, then use whatever means. Like text me, message me on Facebook, whatever. If I'll see your message and you're watching this, you can participate, right? And let's see here. It looks like I got a comment on the show from a club member. Okay. As a club member letting me know. She also does ham radio stuff, and I guess they moved their meeting, so she can't make it to the show. All right. Let's see here. Negative means less attenuation, and then therefore brighter. Yep. Well, anybody got any other astronomy questions? Any topics? It doesn't have to be a question. If there's just a topic you think is cool and we should talk about, definitely drop that in the chat. Like I said, I try to go off of y'all's interests, what you guys want to talk about, what you want to know. We talked about the Southern Hemisphere constellations. We talked about the cosmic ladder and measuring distances in space. I guess for now I can branch off of that topic a little bit and start to answer, given that... Ooh, Artemis. Cool, we could talk about Artemis as well. I was going to say, given the cosmic ladder, we could talk about how far things are. But you mentioned Artemis, and that is a really cool topic that I meant to bring up earlier. So, the Artemis 1 mission finally launched. If I bring up our visuals here, I'm sure there's going to be a picture of it on Wikimedia Commons. Artemis 1. Let's see here. Yeah, buddy. NASA, Bill Ingalls, public domain. Cool. This is public domain. I ain't got to be scared about this one. Look at this guy go. Oh, man. I watched the video later. I didn't get up early and watch it. I wasn't in the area. I could have probably pulled out binoculars and seen it, in the sky from where I live, obviously, but I just didn't, and I kind of regret not doing it, but that's okay. There's going to be more launches, fingers crossed. Man, I thought they never launched this sucker, but they finally, dealt with some of the leaks and stuff that they had, and they managed to launch it. Gosh, I just can't get over. Look at this flame column, man. This thing is just putting out heat. Oh, my God. So, yeah, we could definitely talk about the Artemis, man. So, I think right now, to the best of my knowledge, that I'll have to check, actually, what the mission status is. It might still be in orbit. I'm not sure. If anyone knows the mission status, like where is the vehicle right now, I'd love to know. We'll not actually orbit the moon, but we'll orbit like a Lagrange point off to the side of the moon. Yeah, that's what it's going to do that. It's going to go to the L1 point? I'm not really sure. And it's not going to stay there. It's basically just going to kind of loop around there, and it's going to come back. It's on transit now. Cool. So what that means, it's already done. It's a TLI burn, translunar injection. So if you're not familiar with how a moon mission goes, because this could very easily become a rocketry channel if you guys want. In fact, I kind of want to do a live stream of Kerbal one of these days and talk about rocketry. Who knows? Maybe we'll do it one day. But that might be a fun episode. So what they do is they launch this thing and they park it in orbit around the Earth. And then at a certain point, they accelerate. Because if you're in orbit of a body and you accelerate, the opposite side of the orbit stretches out, right? And if you stretch that out enough, your orbit will intercept the moon's orbiting and you're coming, and you meet up with the moon, and then its gravity is felt more strongly than the Earth. So if you slow down enough, it'll capture you in an orbit, right? And then you can accelerate again to leave the moon, and the Earth will bring you back home. So that burn to leave Earth orbit and start heading towards the moon, they call that TLI, translunar injection. You get injected into a translunar orbit, an orbit that will take you to the moon. And so they did TLI, that is saying, and they are on the way to the moon. About a month or so before heading back. Oh, really? It's going to spend about a month or so out there? I didn't know that either. Man, I know less about the Artemis mission than my dad does. I should, like, he should download OBS software and take over here and tell us more. But yeah, man, I can tell you about how the rocket works, right? If you guys somehow didn't know, I am. Can I show it to you guys? See, the only problem is the angle is. There we go. I am obviously a huge fan of all things rocketry and space, especially when it comes to going to the moon. I was not born yet during the Apollo missions, and it is a big regret that I will never see a Saturn V rocket launch. That makes me sad because I love the Saturn V rocket. I've got models of it here in my room that I'm not going to bother getting out. I am just absolutely in love with the Saturn V rocket. But for me, the Artemis is the closest I'm ever going to get to watching a Saturn V. So at some point, because they're only going to launch a few of them, they're not going to launch a bunch of them. At some point, I need to get down to Kennedy and watch an Artemis launch to make up for the fact that I'll never get to see a Saturn V. Someone said the rocket at launch had 8.8 million pounds of thrust. That's correct. I do remember that as well. 8.8 million pounds of thrust coming out of that rocket. Absolutely outrageous. The way that the rocket works, if you're not familiar with the design, we could talk a little bit about the design of the rocket. For one thing, the Artemis is actually designed to reuse excess material for the space program. For the space program, for the shuttle program, right? So it actually does reuse shuttle parts. These two on the side are what we call the SRBs, or the solid rocket boosters. This bit in the middle is the orange external fuel tank. A space shuttle would have been bolted onto the side here, and then everything above here, this extra bit is an extension with more fuel, I think, and then this is a special adapter right here. And then the spacecraft is up here, and the launch escape system tower. So one thing that makes the Artemis kind of interesting to me is the fact that this central thing is just one enormous stage. Usually with rockets, you will stage them off in sequence because every time you can drop weight from the rocket, you're saving yourself in terms of materials, right? Because you have to have enough fuel to generate the thrust to move the fuel. More fuel requires more fuel to move. Anything you can do to lighten the rocket is going to lower the overall amount of fuel that you need to move it. Or if you keep the fuel the same and just stage it out, you're going to increase the payload size, right? Because you're doing it more efficiently. But the Artemis just has one gigantic stage going down the middle, and I find that odd. As somebody who's played a lot of Kerbal and designed a lot of rockets, granted, I don't work for NASA, I'm just some guy. That seems wild to me that they do that in a single stage. But I'm guessing it's just to make the most out of the recycled space shuttle parts. But I would have thought that at least this maybe have some engines in here and have this be a stage and get to dump this big tank. But no, this whole stinking thing is just one giant stage. And that just seems bananas to me. But it does have RS-40 engines. It's got like 4 of them down at the bottom. Putting out some pretty serious heat. And then the solid rocket boosters on the side, the SRBs. So there's 2 kinds of rocket fuel that you can do. 2 major kinds. And then within each kind, there's, of course, different chemicals you could use. There's solid rocket fuel and liquid rocket fuel. So I'll find in the Saturn V, I tried to show some people at work the same thing, which is why I already know. That the Saturn V rocket cutouts on Wikimedia are better. Cutaway. Here we go. So this is going to kind of show us how it was on the Saturn V. Again, this is NASA public domain imagery here, so cool to use. All right, so if we look and we zoom in a little bit on this, you'll see that inside of that big tube are actually these big tanks. There's 2 of them here. Right, for each of the stage, right? This second stage has 1 tank, but it's actually divided into 2 halves, right? Third stage has a similar kind of thing, like a big tank, but there's a membrane dividing it into 2 parts. The reason why each stage of the rocket actually has 2 fuel tanks is because the liquid fuel rocket uses 2 components. There is a combustible fuel, Usually RP1, that's rocket propellant 1. You'll often hear it called kerosene because it's a derivative of kerosene. It's a kind of kerosene. And then something called the oxidizer, which will either just be liquid oxygen or might be something like tetrazine, right? Where it's got nitrogen, because nitrogen also works as a good oxidizer. So a combustion reaction is a reaction between a combustible hydrocarbon and something that oxidizes that reaction. In atmosphere, that's going to be the atmosphere of the Earth, the oxygen in the atmosphere of the Earth if you light a campfire. But if you're going to shoot a bunch of fuel into a rocket engine and you shoot in the oxidizer with it, you can maximize that reaction, right? And have it be a much more efficient reaction than if you just try to burn it and let the Earth's own atmosphere fuel that. Especially once this rocket gets up to speed, it's going to be hard for it to even suck in the air to do that. So they carry their own oxidizer. But the advantage of this system of having liquid fuel and oxidizer is that you can control the throttle of these engines. You can either just shove more fuel into them or not, right? You can pump more, you know, speed up the pumps or slow them down. The disadvantage is the amount of thrust you get out of it. But liquid engines, they are efficient in thrust, so you get a lot of thrust for the fuel over time, right? Your fuel lasts longer, and you can throttle it, and you can also vector the ends to direct that a little bit and steer. Solid rocket boosters, as you can imagine, they use a solid fuel, SRB cutaway. So this diagram shows, and real fast, this is this person, public domain from NASA. So a solid rocket booster, if you look in this picture here, the shaded bit is actually the fuel, and you'll notice there's an open channel running all the way through the fuel, and it's shaped. You can modify the shape of this, and that'll change the properties of how it burns. But other than that, you are completely at the mercy of the rocket once you light this candle, right? You cannot throttle it. You cannot shut it off once it gets going. You can't really steer the nozzle either, to the most part. And what'll happen is the flame goes all the way up throughout this whole thing, and it burns from the inside out, right? Is how the solid fuel burns until it basically the fire just reaches the outer hull of this thing, and it's completely burned out all the fuel that's in it, right? As you can see, this is the cutaway view, and then here's the more solid view. You can see it's like a solid tube running through there. The advantage of solid rocket fuel is that it produces a lot of thrust. It kicks hard, right? It kicks like a mule, but it's not super efficient. So over time, you don't actually get as much thrust for your fuel as you would from liquid fuel, but you will get a ton of kick. There have been experiments to do rockets that are like solid all the way up, but for the most part, the general thought in rocketry is that main stages should be liquid fueled so you can control them. Solid stages should be bolted onto the side so you can ditch them if you need to, right? So the reason why you might want to combine the two in something like Artemis. I just realized if I just search Artemis, I'm going to get the Greek goddess. Artemis 1. Here we go. There we are. There's a good picture. Joel Kowski, public domain, NASA. Gotta attribute these. I don't know if I'm doing it right, but all right. So these two solids, they actually ignite all the engines at once, right? And it takes off. These two solids provide a hefty amount of kick to get this thing up off the ground and high into the atmosphere, right? Because the first thing you're trying to do is overcome the Earth's gravity and get going. And in the lower part of the atmosphere is very, very thick. It's going to provide a lot of drag, and you haven't yet accelerated up to speed. So it's going to be really hard to get this big, heavy rocket going. And that's where solids are useful. They can give you a ton of thrust and hurry up and get you through the worst part of the atmosphere up to where things thin out, right? And then once you're up there, you can ditch the solids and just use liquid fuel, which is more efficient for the remainder of the journey. And that's how the Artemis works. So the Artemis spacecraft, or the Artemis rocket, I should say, the spacecraft at the top is the Orion. The Artemis rocket, that's the mission profile. It launches. Those solids will burn through quickly, while it gets pretty far up, and then those will come off. And they still, it's interesting, they actually detach them while they're still burning a little bit. So they still have a little bit of thrust, but you'll see them kind of fly off, right? And then the middle part keeps going. And then eventually it burns through all of its fuel, and it's going to ditch this spacecraft at the top, which has its own fuel supply and its own engine, so that it can do its own maneuvers and things. I'm not sure with the Artemis program if this gigantic central stage is entirely consumed once the thing is orbit, or if they use some of this to get to the moon. Given the fact that the Saturn V rocket used its S4B stage at the top for translunar injection, and it had a lander and everything. Although this Orion capsule is much bigger, my guess would be that Artemis doesn't need all of this just to achieve orbit. My guess is that it would probably use some of this for TLI, but I'm not sure about that. I'd have to look into that because I am really curious what the exact mission profile is for an Artemis mission. In fact, let's see if we can find out now. Artemis 1 or Artemis mission profile. Let's just see if there's like an image that shows. Yeah, here we go. Cool. So let's find out. So here we see a good diagram of what I was talking about. Oh, hold on. Let me make sure. This is public domain from NASA. Okay, cool. NASA just killing it tonight on public domain. So the Artemis launches. The two solids are detached. You see there's these little jets right here that kind of push it away from the rocket for safety. The launch escape system tower also gets removed. So what this tower up here does is if something goes wrong with the rocket, it can yank the capsule off of it and just blast that away to safety. There's little rockets on there. And then we have MECO, that's main engine cutoff. And then separation, perigee rays burn, TLI burn. Oh, wow. Okay, yeah. So never mind. I was wrong. The entire central stage gets consumed in orbit, right? And then and in fact, if I'm reading this correctly, this stage comes back to Earth, which means it doesn't even achieve orbit. They have to detach the spacecraft, and the spacecraft actually does a burn for separation. And you see right here, perigee rays. What that means is, like, if you're tracking the orbital path of the rocket, if it hasn't achieved orbit yet, that orbital path, collides with the Earth. Perigee is what's called the low part of your orbit. So the perigee rays are burning to raise the perigee outside of the Earth's surface, so your orbit is an actual circle. So that, in other words, they're completing the orbital burn. So it looks like the spacecraft itself does that, right? ICPS stands for, I forget. It's the name of this spacecraft. It's the something. And then it TLIs, and then the Orion separation, and then it looks like there's more to this picture. I'm guessing the rest of this picture kind of depends on what you're going to do once you get to the moon, right? And then, let's see, that's Artemis 3. There's Artemis 4. Do we have one for Artemis 1? I don't think so. It doesn't say more results found. Yeah, we don't have... Okay, I'll have to look it up later, what the plan is for Artemis 1. Dad was saying it's going to kind of like orbit like a Lagrange point. That's probably right. I'm not sure. But, yeah, good question about the Artemis, man. That's another really cool topic. Does anybody have anything else we can talk about for the next 26 minutes? Got to open it first before you can drink it. The problem is once it gets so wet, it's hard to open that little... Come on. I'm going to die of thirst before I get this stupid thing open. There we go. I should leave it open. I don't know. Like, I'm worried I'm going to spill it. But, yeah, does anybody have any other topics of anything we can talk about? Well, I guess I'll do my my usual housekeeping end of stream stuff while I wait for any new topics to crop up. I want to remind everybody that, again, I am representing the Northeast Florida Astronomical Society. Let me go to our homepage and let that load real fast. Our logo always hesitates and takes a while to load. Not sure why that is, but our webmaster is watching right now. Maybe he can answer that. But I'm I'm going to let it load because it has our web address on it. So it's an easy way to show it to you guys and put it on the screen for you. But we are NEFAS. Here it is, nefas.org. That is the Northeast Florida Astronomical Society.org. We got this great picture of what I'm assuming is the Jacksonville skyline with Saturn. I haven't compared it to figure out which buildings these are supposed to be. If I don't know if these are random buildings. I hope it's our skyline. It would be really cool if it is. You can go to nefas.org and oh man, planet Earth from Orion. Hold up a second. Sorry, we just gotta look at this, guys. The Orion spacecraft, they snapped a picture of the Earth. Oh, so cool. Okay. Anyway, got distracted. So we are nefas.org. We are the astronomy club here in the greater Jacksonville area. Seriously, there aren't any others. Well, some of the colleges have them, but like we are like the astronomy club here in Jacksonville. If you are interested in the science of astronomy, check us out. Check out our calendar, especially for upcoming events. Just want to remind everybody that this weekend we're going to have a possible dark sky night. And John, I don't know why we don't have another one posted here for the 26th. Shouldn't it be these 2 weekends? Get on that if you don't have that on the calendar anyway. But if you are a member of the club and you get my emails, then you'll know when we're heading out. I will say, and I didn't mention this earlier, the Dark Sky is not an outreach event. That's not to say that it's not open for anyone who wants to come. And that's not to say that we're not friendly with newcomers. And it's not to say that nobody will invite you to look through a telescope. It's just to say that outreach is when we set up our telescopes and they're all there specifically for people to look through, and it's outwardly focused, right? That's our opportunity to do education and outreach. The dark sky observing sessions, most of our club members are out there to do their own astronomy because we are astronomers and we want to look through our telescopes too, right? So this is the one thing we do for ourselves. We do everything else. We set up telescopes at schools, churches, museums, etc. And then this is us getting out and observing. But that said, if you want to get under a dark sky, if you got your own telescope or you just want to kind of hang out and look visually or whatever, you're still totally welcome to come hang out with us. We love having people join us out there. We're not trying to scare anyone away, but just know that that's the environment. Know that it's very remote. It is a wild place. There is wildlife, but we go in a group so that we're safe. And there's no bathroom facilities and there's no cell service. So just be aware of that. We try to post a go, no go on Facebook, but the best way to find out about it is if you're a club member, you'll get the email. That's coming up this weekend. And then the only other thing really to talk about coming up is Hannah Park. First Saturday of December, Saturday the 3rd, we're going to go to Hannah Park, and hopefully I will not be sick again like I was last time. Fingers crossed. And we're currently not double booked that night, so there's no reason that I shouldn't be there for that one with my laser pointer ready to go, giving a tour of the night sky and talking about all these wonderful things that I love to talk about. This one is the one to go to if you want to look through people's telescopes, ask them about their equipment, and this is outwardly focused. This is something we do for the public as a service, right? As part of our tax-exempt status, and just because we love it. We're just passionate about it, right? This YouTube channel was started because we couldn't do this during COVID, and I missed doing it so badly I started a YouTube channel, right? So that's why we're out there. That's why we're doing it. And then the following Saturday, Saturday the 10th, is the NEFAS holiday party. We're going to announce the winners of our astrophotography contest and have a really good time for our club members. And then that's pretty much it for the month of December at present. We don't really have any December outreach plan, but of course, it's the holidays and that kind of thing. So yeah, if you are interested in the club, you can come to our website. There's a membership tab. You can click Join NEFAS, new or renew. So if you're renewing your membership, you can do that here as well. Fill it all out, pay through PayPal. These are the membership levels, right? Students and seniors, it's $20. This is per year. Individuals is $40. Family is $50. Family, we just consider that any two adults and whatever kids they happen to be in charge of. That's our definition of family, right? All families are part of our family. Be a part of our family. And then the benefactor level, you don't get anything different from any of the other levels for being a benefactor. The only real difference is we mention you in the newsletter every month, and it's just a way to give more money. That's all it really is. So if you just really believe in the club, you just really want to give to the club, you can be a benefactor, but you don't get anything different, so don't feel like you got to do it. It's just something that that some of our members do because they've been with the club for a really long time. They really want to support us, and so they do it, and that's all it really is. But otherwise, no different from the other memberships. Membership in NEFAS allows you to do a lot of cool stuff. You can borrow our telescopes. We have a telescope loaner program where we have telescopes that belong to the club itself, and you can check them out. And these aren't cheapo, dollar store gift shop telescopes. We've got 6-inch Dobbs, right, and other fancy stuff that our club members can borrow. Literally check it out like a library book for a month and bring it back. It's a really good deal for people that are doing like the family membership. You got kids and you don't have a telescope and you're not sure. Joining the club for $50 and borrowing one of our 6-inch telescopes, you can't beat that deal with a stick, man. That is a lot of telescope for $50. Now, granted, it's a yearly membership, but I mean, it's a really cool deal for families and for anyone else. Also, you're a member of the Astronomical League if you're a member of NEFAS. So if you want to start getting some of the certificates, right? Start wearing those pins like I wear on that hat that I wear to our outreach events that's covered in pins. Our club members can participate in those because you're also a member of the Astronomical League. You don't have to enroll separately, right? And of course, you can come to our board of directors meetings as well and have your voice be heard. And sometimes when we put things to a vote, obviously only members can vote. So that is some of the information about membership. And when I say put things to a vote, I mean there are times where we vote on something in the board of directors meeting. We vote to put it to the club members, and the club members then vote at the next general meeting. To clarify, so that is about membership, and that is a little bit about the club. If you live in the St. Augustine area, check out the Ancient City Astronomy Club. Oh, gotcha. John is mentioning, okay, the reason why that other dark sky event is not scheduled is because it's after Thanksgiving. I might be thankful for a dark sky if I head out there. And I might have to be thankful for clear weather, right? Here's hoping that we'll have a lot to be thankful for that weekend. Like I was saying, the Ancient City Astronomy Club is another group of guys out in the St. Augustine area. So if you live in the St. Augustine area, definitely check them out. You can be a member of both clubs, but we don't try to snipe their members and they don't try to snipe ours. So I always tell people in St. Augustine about them because they're a great group of guys and you should know about them. And I think you couldn't join a better club unless maybe it's ours. Kidding, of course. And I am a member of both clubs, so they're both my club. So actually, I might not still be a member of ACAC. I might have to check if I need to renew. January meeting will be a help session for folks with new telescopes. Ooh, Mike, good point. So I usually only talk about a month out during these live streams, but this is a big one, so this is a good one to advertise now. So getting back to our calendar, our January meeting, right, on the January the 13th is going to be a meeting on how to use your new telescope. Now, I'm sure you can guess why that might be the theme of that meeting. It's usually the theme of the first meeting we have every year because people get telescopes for Christmas, right? You get a telescope for Christmas and you don't know what you're doing? Come to this meeting. We will show you how to use that telescope. Free of charge, free service we offer. Obviously, I think the best accessory you can get for your telescope is a club membership. And I'm not just saying that because I'm membership director. I'm saying because I believe it. Ever since joining the club, my skills as an observer have blown up. Being a part of an astronomy community is the way to learn, man. It really, really is. But barring that, if you get a new telescope, at least come to this general meeting in January and let us teach you how to use it. We'll teach you how to set it up, how to find stuff in the night sky, right? What different eyepieces do, all that good stuff. We'll get you fully up to speed on it so you can take that joker out whenever you're bored, check out the sky, and just enjoy the beauty of the universe. Like tonight, right? Here in 15 more minutes when the live stream ends, get outside. And if it's not cloudy, I haven't looked. I don't know what the weather's going to look like. But if it's clear, man, you can see Jupiter, Mars, and Saturn tonight, right? And the Andromeda Galaxy and all kinds of cool stuff. All that cool stuff I was talking about before. But like I said, if you get a telescope for Christmas, or you know someone who got a telescope for Christmas, or you plan on buying somebody a telescope for Christmas, highly recommend this meeting as a way to learn how to use that telescope. So good call, Mike. Mike, by the way, you see him down there in the chat. Or just help with your existing scope, as he points out. That is our club president there, Mike. John, our former club president, Got a lot of royalty there in the chat. Um, but as Mike points out, it doesn't have to be a Christmas present. Obviously, if you need help with your existing scope, we can do that too. Uh, a good friend of the family, my dad's friend's widow, unfortunately, he passed away. She has his telescope, and she was like, Dave, I don't know how to use it. She joined us out at Fort Clinch for an outreach event. I taught her how to use it, and then she had a line of people, and she was using it to show them Jupiter that same night. So we will set you up, man. If you go anywhere we will set you up. But that is the theme of this next meeting. And so there are people who can tell you from experience that we will definitely set you on the right road when it comes to that. John mentions the Leonid meteor shower. So let me see what's going on with the Leonid meteor shower. That's tonight. Okay, good to know. I am the worst at keeping track of meteor showers. If you go out tonight and you look for meteors. They may be Leonid meteors. What do we mean when we say the Leonid meteor shower, right? Well, meteor showers are named. This could be something we talk about for the remainder of the show. Meteor showers are named, and bear with me, man, I've got... So my sinuses are still blocked up. This weather's wreaking havoc. And that pressure buildup in the head, like my voice resonating through that, like by the end of this thing, my head is now pounding. The things I do for you guys. But yeah, so that aside, when we name meteor showers, we name them for what's called the radian. In other words, we name them for where they look like they're coming from. Oh, you know what? Let me get back to tonight. There we go. Cool. All right. So the Leonid meteor shower is so called because the meteors will look like they're coming from the constellation Leo. So I bring up their constellations real fast. There's Leo, right? So all the meteors are going to originate from Leo and sort of shoot out. That being said, it doesn't necessarily mean that every meteor trail is going to literally start off in Leo and then move. And actually, if I zoom in, is it going to show me the radian for that meteor shower? Because usually meteor shower radians are indicated on the software. It's not going to show me? Okay. Well, somewhere near Leo is going to be where they are going to appear to come from. But actually what's going to happen is you'll see meteors all over the sky. So you might see one go like over here, and then you might see one go like over there. But if you were to run them backwards, they all are going to appear to point towards Leo, right? So the radian doesn't necessarily mean it's going to start in Leo and literally move out, right? That line will go from Leo, but the part of it that you might see will be over here, right? Or down here, or up here, or that way, right? They're going to all seem to go different directions. But if you were to sort of like imagine running it backwards, the point of origin would be in Leo, right? And that is the Leonid meteor shower. And we call the meteor shower after the constellation. So Leonid from Leo. There are also what are called like the Orionid meteor shower. There's the Perseid meteor shower. The Quadrantid meteor shower gets its name from an outdated constellation that's no longer around. And I forget what modern constellation it appears to come from. But yeah, those are the different ones. John, you seem to know more about it than I do. Is the Leonids... Are we expecting a good one for the Leonids? Are they saying it's going to be a nice big bright one? Lots of meteors? While I give you a chance to answer that, I'm going to quickly talk about why we have meteor showers and how we can predict them and predict their quality. So, if you guys know what a comet is, and I'm sure you probably do, or maybe you do, right? The whole point of this show is that maybe you don't. That's why we're here. So, a comet is a big chunk of ice and rock. The reason why I'm saying you probably know, because the people in the chat are all in the astronomy club, but any of you guys watching this later, you may not know what a comet is, but it's a big chunk of rock and ice out in space, right? So we got a big picture of this one, Hale Bop. This was a Creative Commons attribution from Andy Roberts in London. Thank you, Andy Roberts. And so here we see right in there is where that chunk of ice and rock is, and then when it gets too close to the sun, the ice sort of steams off, right? It doesn't melt. It skips melting entirely and just goes straight to being steam. And then the solar wind always blows that away. So no matter what direction a comet is headed, the tail always points away from the sun. So sometimes the tail is actually in front of the comet, if you can imagine that. But also there's a lot of rock and dust and stuff in that comet. So the comet will form two tails. This blue tail is actually the steam. I know that threw me off at first too. I thought it would probably be the white one, but it's not. The blue tail that you're seeing here is actually the steam that has been ionized, and so it's following the magnetic field line from the sun. And then this bright one here is the dust. And the dust is just reflecting a whole lot of sunlight and is more visible and is not bound to the magnetic field line as strongly as the ion tail. So it's bending in sort of different direction based on the trajectory of the comet and the solar wind particles from the sun blasting all that stuff back. But all this stuff you see coming off of here, that's little bits of rocks and things, right? Little bits of dust. Well, that all gets left behind the comet when it completes an orbit. So the comet orbits around and just leaves all this dust in its wake. Well, later, as the Earth is orbiting, Earth will pass through that cometary material, and that stuff will burn up coming into the atmosphere. So that causes a meteor shower. Meteors are just things burning up on their way into the atmosphere. And in spite of the fact that they look like they shoot across the sky, they're actually headed straight down. Right, but you know how like when you look at railroad tracks, they appear to converge? That same effect is kind of at play. So everything coming straight down at you from the sky is going to look like it went off sideways, right? Just because of the vanishing point perspective. But there's always little bits of, dust and stuff in Earth's orbit sort of all the time. And so you get meteors all the time. They just happen. But a meteor shower is when we're going to pass through what's left from this comet. And so we're going to get a whole bunch of it all at once, and that's going to be the meteor shower. And based on what the comet did, we get some idea. Like if the comet was kind of like a bit of a disappointment, sort of went, and didn't put out a whole bunch, then there's not going to be much to pass through. And it's going to be kind of a disappointing meteor shower. If that comet split in half, man, and it just threw a bunch of stuff and it lit up the sky and made the news, then we might be getting a really good meteor shower out of it, right? So that's why we can not only predict when they're going to be and say exactly when they're going to happen, but even predict, have some means of predicting the quality. Paul said it's one of the more major showers and is generally a good show. Okay, cool. The Leonids may be worth watching. If you are going to stay up late tonight, maybe drive somewhere dark. I will say a lot of meteors are not very bright in reality. Light pollution often overshadows them. You get somewhere dark, you see more of them. But that may be worth doing. When is the peak? Do you know? I didn't think to check when in the night the peak is going to be. Let me look at that. Meteor shower peak. The problem with meteor showers, you have to stay up late, right? You usually have to get up really late or be up early. So 3:49. Oh, hold on, that's the wrong one. 22:49 Eastern. So, oh my God, basically right when this show is over. So that's not bad at all, right? Oh no, that's when Leo's gonna rise. Okay, hold on. When's the peak? Tell me when the peak is gonna be. Yeah, okay. The best time is gonna be 6 a.m. There we go. So they're saying 6 a.m. is gonna be, yeah, it's gonna be a good time. But the dawn is gonna erase it almost immediately after. So, what you might do then is set an alarm and get up early. Get up at like 5:30 maybe. Get out and watch a good half hour of the meteor shower. Watch it build up and look really cool, and then maybe call it a night. So that might be, or get ready for work, I guess, right? You're gonna go into work. Excellent, good point, John. Thank you for bringing that up. So that might be worth a look as well. Well, it's 9:25. I don't really know what I could spend 5 more minutes talking about. So now feels like a logical time to conclude the live stream. Plus, like I mentioned, my head's kind of killing me right now. John says, sound like a plan. Yeah, getting up at 6 a.m., right? Let's do it. Not me. I've seen meteor showers. I'll see more later. I'll catch it next year, maybe. But I know I'm a terrible astronomer. That's not like a real astronomer. But I do want to thank you guys again so much for watching the show. Both those of you guys who are watching it live, and also those of you who are watching this later um, on recording, right? You're watching this after the fact. Like I said, these videos I'll often have like 8 or so people watching it, and then I'll come back and check later, and there's like 100 and something views, right? So there's people that hop on later, and I really appreciate those. You people as well. I say those as if I'm not talking to you, but in the future, appreciate you. Um, but I really do. I appreciate all of you guys who watch this show. This honestly just started off as a thing I was doing because I really missed getting out and talking to people about space because we had a pandemic. But now I'm just continuing it. People really seem to be responding to it, and it honestly just flatters me so much and just makes me feel so appreciative that you guys are getting benefit out of this, and you're encouraging me to keep doing it. And I'm only doing it because of you guys. If you guys didn't care, I wouldn't bother. So you make the channel, and just want to thank you guys so much. And I also want to remind you guys, of course, as always, look up, right? Look up in the sky, and if you have outdoor lights, make sure that they are aimed downward so that they're not contributing to light pollution. And get out there, right? That's my big thing. Get out there, crane your neck, and look up, because there is a beautiful show on display above our heads every night, and it's a shame not to get out and look at it, right? I might even do so after the stream. But thank you again so much, and have a wonderful night.